and particularly the cool format of this, the idea that this is going to be the takeoff for a point to learn about lots of different beautiful ideas and dynamics. Thank you to Lauda, UIC, and I'm sure I'm missing other folks, but in general, thank you to the organizers for not only having me speak, but the really, really cool format of the meeting. And I'm excited to get to know many of you, not just today, but down the road as we talk and learn more. And thank you to Grace, who's going to be helping with the reading group that grows out of this, hopefully. Yeah, I think chat is great. I'm keeping an eye on the chat as well. And that's probably the quickest way to ask questions. And I'll definitely try and pause. I'll pause and ask for questions as well, but I will keep an eye on the chat. So let me say, so of course, my title is Ergodicity for Billiards. There's a key word here, rational prisms. So I need to tell you what a rational prism is. But secretly, and this is, I should say that what I'm going to talk about today is joint work with Nicolas Bedaride and Pat Hubert and Pascal Hubert. But the secret agenda for today is so of course I want to tell you a theorem, but what I really want to tell you about is this beautiful big idea. Agenda, tell you our theorems. That's of course part of the agenda, but the real agenda is to tell you a beautiful idea of Furstenberg's. And this idea may in some sense go back to Auslander, according to Brian Craw, but also the subtitle of this talk could be Why Weak Mixing is Cool. Okay, though maybe I'll tell you about weak mixing and then you can tell me if it's cool or not. So I think it's cool. I have a new appreciation for it having worked on this project. Okay, so let me start, like many things in dynamics too, with a really simple toy physical problem in Newtonian mechanics. So toy problem in Newtonian mechanics. So we'll start general and then we'll get way more specific. We'll start with P, a polyhedron. So this is sitting inside of R3. I want to think about it as sitting inside of R3 and it has some non-empty interior. So you could think of your favorite polyhedron. So for example, you could think of, I don't know, a cube or a rectangular prism is what I've really drawn. Or you could think about something like an octahedron, right? My drawing skills don't really extend that much further than this. And what we're going to do is we're going to play billiards inside of P. So that is, what does that mean when we say billiards? We're mathematicians. So we're going to think about a point mass moving at unit speed with elastic collisions with walls. And by the way, just a quick question. I have my window open here just for breeze. Is the noise from outside, I can hear a little bit, is that bothering you guys or is the audio reasonably okay? It's okay? Great. All right. Okay, so point mass moving at unit speed with elastic collisions with walls. And for right now, we're going to kind of ignore collisions with edges and vertices. And the question we're going to ask is, what is the long-term behavior of trajectories? So, for instance, certainly, so this is a flow. This is a flow kind of defined on P cross S2 to itself, right? We have a point and a direction. Unit speed means it's really a direction, and we sort of bounce around. Maybe we have some point, and it starts and it hits a wall and it bounces around. This is not a good drawing, but it's kind of bouncing around off the walls, and we could ask what happens to it in the long term. And it's pretty clear that, for instance, this billiard flow preserves Lebesgue measure. So one question you could ask is Lebesgue measure, so a little sub-question one could ask is question, is Lebesgue measure ergodic? Is this flow ergodic with respect to Lebesgue measure? Is Lebesgue measure the unique preserved measure? Is it uniquely ergodic? That's another phrase. And we'll define ergodic and uniquely ergodic a little bit more carefully in a moment. But now let me just say, in this generality, this is a really, really hard question, and we know very, very little in this generality. So there's a few things we know, but I don't want to get into a long literature survey. What I'd rather do is get into some very special cases where we now can actually say something. So maybe I'll just say, in general.
Sorry, can I interrupt for a second?
Of course, Noel.
Quick question. Are there periodic orbits?
Great question. I don't know. In that generality, it's really hard. And in fact, let me even say, let's go down one dimension, right? This question is maybe too hard. Or too hard is the wrong word. It's hard, and so it will give us research problems to do for a long time to come. Maybe just for the grad students, I'll share stories. I remember complaining to my postdoc mentor, Yair Minsky, once that some problem I was working on was too hard, and wouldn't it be easy if everything simplified? And for the experts in the room, it was, man, it would be nice if Teichmüller space was actually hyperbolic. And he looked at me and he said, the reason you have a career is that it's not, because you can actually work on problems that would be trivial if this was. So it's good that this problem is too hard, because it's going to give us all a lot of things to work on. But for right now, if we want to say something immediately, and so let me get to Jeff's question, let's even go down a dimension. Let's go down a dimension to just a polygon, which I'm going to also denote by P in R2. And we just play billiards in here. Again, point mass. I should have also said in the 3D case, right, I'm talking about no friction or no air resistance. There's no gravity around. It's just you're moving in a vacuum. And here on this two-dimensional thing, again, no friction. So we're really idealizing things. So we're really, really idealizing things. So here's an open question. Is there always a periodic trajectory? This is open even for triangles. Now, I should mention there's results for triangles. Rich Schwartz proved that for every triangle of angle less than or equal to 100 degrees, you can do it. And this has been extended recently, and I'm going to blank on the names. So I think now we're at 112 degrees plus. If you get bored during this talk, try and prove it for angles, for acute triangles, for angles less than or equal to 90 degrees, that you always do have a periodic billiard trajectory. But in complete generality, this is wide open. And I think it's probably fair to say, and I think the experts in billiards would agree, that right now this is kind of beyond current technology to answer in complete generality, which is really kind of it's just an indication that, if someone says, oh, we kind of know Newtonian mechanics, you can say, sure, in some sense, yeah, we know the rules of Newtonian mechanics. But there is lots of mathematical implications. This is incredibly simple. And I wanted to start with this because this really highlights one of the big ideas in dynamics, which is a lot of dynamics is motivated by incredibly simple physical problems. Okay. But having said why this is all too hard, let me now talk about a class of polygons where we do understand things. And that's going to motivate a class of polyhedra where we can say something. So, rational polygons. And those of you who've heard me give talks before know that I love this story about this kind of classic joke about this person who is looking for, sort of on their hands and knees under a streetlight looking for something, and someone comes up and says, hey, did you lose something? What are you looking for? And the person says, oh yeah, I lost my keys. And the second person says, oh, did you lose them over here? And they say, no, but the light's good over here. So now we're going to be the people who, yeah, okay, of course we want to understand general polygons or general polyhedra, but the light is going to be much, much better when we make this assumption of something called rational. And one definition of rational is simply that the angles are in pi q, okay? And you can take that to be your definition, just rational multiples of pi. So for instance, you could have something like a square or an L shape. I'm not insisting that my polygon be convex. You could take, maybe a nice right triangle with maybe some 45, 45, or even, different kinds of nice right triangles with rational angles. You could take 30, 60, 90. You could take all kinds of, as long as, so this is pi over 2. So maybe this is, pi over 2, some pi, p over q, and then whatever this has to be left over, etc. You could take, sort of regular n-gon. So you could take a hexagon or a pentagon. All of these are rational. And what's cool about rational polygons is they have the following. In fact, this is an equivalent characterization. If you look at the group generated by reflections in the sides, okay, so that group is going to have a bunch of translations in it. So we quotient out by translations. Modulo translations, this is finite. In other words, if you take the lines that define the polygon, move them to the origin, and look at the group generated by those reflections, that group is finite. Again, if you get bored in this talk, you can try and prove that equivalence. That's just all you need is a little bit of Euclidean geometry. All right. So why are these polygons great is studying billiards in these polygons connects to a really rich field called the study of linear flows on something called translation surfaces. Okay. So translation surfaces are some of my absolute favorite objects in mathematics. And let me explain how you have this connection. This connection happens through something called unfolding. And before I give you the definition of a translation surface, let me show you how unfolding works. And then before we define translation surfaces, I actually want to state our theorems about billiards in what we're going to call rational prisms. And then we're going to connect it back to translation surfaces and these notions of ergodicity and weakness. But first, let me show you what unfolding is. This is definitely a big idea in dynamics. And this unfolding idea, let me just quickly historically say this unfolding, it has many people have kind of discovered this idea. Two people who found it in the West were Fox and Kirshner. This is in the 30s. And then it was independently found by Zelniakov and Katok. Let me just do it for the square. And the idea is what we're going to do is we're going to trade playing billiards for playing Pac-Man. Okay, so or for playing Aliens or any other computer game where you go off one side of the screen and come up the other. So let me demonstrate it for the square. Many of you have seen this before, but I want to do this to you for the students in the room. Let's say I label the sides of my square A, B, C, and D, and I'm going to have some kind of billiard trajectory in here. Maybe that looks like that. So that's the start of my billiard trajectory. Is the pink okay, or would something a little bit lighter be better for you guys on the board?
Lighter is a little bit better.
Absolutely. Let's go. Let's try yellow and tell me if yellow is okay.
Yes.
Is yellow better? Excellent. We'll use yellow. So what we're going to do now, though, is we're going to say, okay, we have our trajectory. By the way, just notice that if I start in a direction here on a rational polygon, this is a square, it's very clear that the only directions I'm going to get are that direction acted upon by this group of reflections I mentioned earlier, which you could, I'm not going to give it a name for right now, but here there's 4 possible directions that you can go in. And so in particular, instead of thinking, already you can kind of see, instead of thinking of the polygon cross S1 as your phase space, you can really think of the polygon as your phase space with a fixed direction. And you can talk about the flow in a fixed direction, and then there'll be 4 directions, but that's kind of okay. There's a finite group, and maybe what we're kind of using is S1 mod a finite group is isomorphic to S1 again. So we're going to start talking about flow in a fixed direction. So now when I go in this direction, I hit a wall, right? When I hit the wall, maybe I'm lazy and I don't want to change direction. So I just want to keep going straight. So now I just flip my table. So I'm going to still use yellow, and I'm going to label the segments 1, 2, 3, 4, 5. And now I'm going to continue. And this is just a copy of segment 2 reflected. And now, because I made a bad choice with where I drew things, I'm going to draw this next guy. So this next guy should be up here, but I'm just going to draw it down here so I have some room. So this is BA and then DC up here. In fact, what I might do is I might, just for the ease of the final drawing, I'm just going to draw it. Sorry, I went back too far. This is 2. I'm just going to draw it down here. DC. When I flip it over like that, it's going to be DC on top and BA on the bottom. And now we're going to have this segment 3 continuing to go straight. And now segment 3 should, sorry, that's the bad drawing. Let's go back one. So I start between, segment 3 starts between B and A and ends between C and A. That's segment 3. And now I'm going to reflect again. And again, what I'm going to do is I'm going to draw this guy just over here, just because it's easier and I'm running out of room on that side, DB, AC. And now 3 started between, segment 4 now starts between C and A, and now it's continuing to go straight, ends between C and D. And hey, look, now I'm just back to where segment 5 started. So I can just kind of keep going. And because if I reflected again, I'd get another copy. If I just reflected, I'd get another copy of ABCD. And so now look at what happens. The way I've made some clever choices of gluing, it's BDDB, BDDB down here, right? This is BDDB, it's CDDC across this way. And then I have ACCA down this side, ACCA down this side, ABBA and ABBA. So in fact, what I get is I get a 4 times larger square with the left side glued to the right side and the top glued to the bottom. And in fact, this is a torus. And what I've done is I have turned billiard flow on the square to what's called linear flow or straight line flow on the torus. And this torus is, well, if my original square was a unit square, this would be sort of on R2 mod 2Z. 2. So if this was, 1 and 1, I've turned it into a linear flow on a 4 times larger square. Now, the exciting thing here is that in general, we don't always get a torus. So, for example, actually, if you were to take the billiard in even a hexagon, you would actually get a genus 4 surface out of this unfolding construction. In general, what you get is a collection of polygons with parallel edges identified by translation, which is exactly yielding a surface. And if the genus of the surface is greater than 1, a finite collection of singular points with angle great equals some integer times 2 pi, where k is something bigger than 1. So so notice when we unfolded the square, when we glue opposite sides of the torus, we have this corner point which collapses to 1 point on the torus, but it's fine. That still has angle 2 pi. In general, for example, if you were to take the pi by 8, 3 pi by 8, right pi over 2 triangle, if you unfold it, now I'm going to tell a slight lie. Please don't call me on it for the experts in the room. It's almost true that what you get is an octagon with opposite sides identified. And you can see several copies of this original triangle in the octagon, right? So if you cut up an octagon into 16 triangular pieces, so if it's an extra large octagonal pizza, each of those pieces is a pi by 8, 3 pi by 8. There's 2 pi over 16 on the inside. And if you take this, you in fact get a genus 2 surface. You get all of these opposite sides identified. And if you follow opposite sides identification here, you will see that all of these 8 corners collapse to 1 point, giving you a point with angle 6 pi at this. Okay.
Oh, sorry. Can I interrupt with a quick question?
Please do, Noel.
Yeah, in the chat we have, what would the translation surface associated to the L shape look like?
Great. Thank you, Joshua, for that question. So Joshua, do you want to know if I play billiards and the L shape, what's the translation surface I'm going to get?
Yep.
Great. So let's think about that for a second before I start drawing pictures. The group generated by reflections in the sides is still the same as the group generated by reflections in the sides for the square, right? Because I just have sides parallel to the axes. So in fact, all I'm going to need is 4 copies. A group has order 4. So if I start with an L and I do unfolding, in fact, if I sort of draw it appropriately, what I get is what looks like what we call a Swiss cross. This is not the best picture in the world, sorry. But you get 4 copies of your original L with the opposite sides identified in kind of the obvious way. So this gets identified to this, this to this, this to this, this to this, and this to this. And if you follow this around, you will actually, once again, it looks like you might have 2 singular points, but again, you'll have just 1 singular point of angle 6 pi. Coming basically from, so this guy is glued to this guy, which is glued to this guy, which is glued to this guy. And so then you have these 4 3 pi over 2s on that, because the other ones actually end up just giving you you can think of them as marked points if you like, but they give you points with angle 2 pi. So that's a great question, Joshua. Thank you for asking it. You can also just start with an L shape and make just a translation surface out of an L shape. So you can just start with this as your polygon, and now you can do these as your identification. So you just start with this, not necessarily play billiards, just do this. And if you do this, you'll also get a genus 2 surface with one singular point. So that's a kind of a fun game to play, is to just draw your favorite polygons and see what kind of surface you're going to get out of this. So all you need is a polygon such that every side has a parallel side of the same length that you can glue it to. And you're allowed to sort of break obvious sides up, right? So here, topologically, what I've drawn is still an octagon. I have 8 sides, even though a bunch of the sides are parallel to each other. Okay, it's hesitate. I don't really hesitate to this. I don't know why I should say hesitate to this. We worked very hard on this. If you're interested in learning more about translation surfaces, Howie Mazur, UIC's own Howie Mazur, and I recently completed a book on this. It's in the the AMS Graduate Studies in Mathematics series, and is, I believe, on sale in the AMS bookstore right now. But it's an introduction to translation surfaces, which will have a lot of the details of this unfolding and a lot of the pictures of it. So, a little advertising. Okay, so keep that in mind. Rational polygon. So far, all I want to kind of hint at is that rational polygons give you these linear flows on translation surfaces. Surfaces which have, and now there are lots of tools and structure, in particular something called renormalization, to analyze these flows. And now I could start mentioning names, but mentioning names, we would be like here for the rest of time, essentially. But let me mention a couple of very, very important names. One is Mazur, one is Veach, and then I also want to mention the names of Kirchhoff, Mazur, and Smiley as hugely important contributors to the start of this subject. There have been a huge number of contributors subsequently, but again, if I get into naming names, these are going. It's going to be here forever. I will mention a few names later on when I talk about specific results, but let me not try and do a general historical background. Okay, so rational polygons are better to understand. So the class. So remember, we wanted to start with polyhedra. There, you could say, is there some notion of rational polyhedra? And the answer is yes. And the generalization you'd want is that the group generated by reflections in the faces is finite modulo translations. But that turns out to be a significantly trickier thing to analyze in 3 dimensions. It's not the same thing as having solid angles which are kind of rational. It's or even sort of dihedral rational angles. It is not the same thing. You can have a polyhedron with dihedral rational angles such that the group generated by reflections in the faces is infinite, even modulo translation. So that's already a big difference between dimension 2 and 3. So okay, let's try and say something. So the ones we're going to look at we're going to narrow down to rational prisms. So what's a rational prism? It's just a right prism over a rational polygon. So what are we going to do? We're going to take some, P in R2 is a rational polygon. And we define the prism, we'll call it sort of boldface P, is just P cross 0, 1. That's it. So I have maybe my polygon in the plane. I take 0, 1, and I just make the prism. So here it looks like some wedge of cheese, but it can look like whatever you want. And now we're going to play billiards in here. Let's play billiards. So this is the situation that we're going to study. And again, I want to emphasize that it is okay, especially for the students in the room, you can study what seems like the easy case, because often the easy case will have lots and lots of interesting and beautiful structure. And in particular, that's what ends up happening here. So let me state two theorems kind of informally. And if we have some time towards the end, I'll try and state them a little bit more formally. So the first theorem, this is ABHH, myself, Nicolas Bedaride, Pat Hooper, and Pascal Hubert, that for most rational polygons P, the billiard flow in the prism P is uniquely ergodic in almost every direction. And in fact, we can say a little bit more. We can say more about the set of exceptions. More about exceptional directions. And so that's one theorem, and I'll try and state this a little bit more precisely. This builds, I should say that there is a previous result of Beck and Chen, which says that if you take almost every point in P and almost every direction, you get equidistribution of the trajectory. So if you look at the billiard trajectory, it spends the right amount of time in each sort of subset of the polyhedron. But ours actually strengthens this and says it doesn't matter where you start, it only kind of matters what direction you go in. And for almost every direction, you equidistribute. And so corollary, maybe I'll put this up here, is for every point in my polyhedron and almost every direction, the billiard trajectory equidistributes. With respect to Lebesgue measure. Okay, so that's one theorem. And then we have a second theorem, which is, and in fact, this is really a corollary of one of our second theorems, is we have explicit examples of rational P and directions so that the flow does not equidistribute in fact, is not even dense, but has fractal orbit closure. And I will show you some pictures at the very end just to hint at this. So the first example, the best example we have is in fact coming from billiards in the heptagon, so a 7-gon. And I will show you some really cool pictures of this. And for the experts in the room, this actually comes, so I'll just maybe quick remark here. This comes from explicitly constructing eigenfunctions for linear flow in the unstable direction of a pseudo-Anosov map with a Pissot expansion factor. The reason I'm going to say all these words is because I think it kind of indicates all the different kind of cool things that you get. You have this idea of what are called eigenfunctions, and that's the next thing I'm going to tell you about. I will probably not get to say what Pissot expansion factor is, but that's a beautiful connection to kind of algebra and number theory. And so the point is you can start with a problem purely that looks very kind of dynamical, and you can end up in all kinds of different places. So let me now just make another remark here, which is that what we'll actually study here is we're going to call is something called linear flows on translation prisms. That's in fact the title of our paper, which it's very funny. We had hoped to have it done by July. Now we're hoping to have it done by January. We'll see. It keeps growing, which is a good sign in the sense that we keep getting together, talking and finding out interesting new things. At some point, we'll have to stop. And I will send it to all of you once it's up on archive, because I know I really hope that we would have it done by now, but it's good that we don't, because we're discovering all kinds of beautiful, interesting new things. But let me just say, what is a linear flow in a translation prism is if I have x omega, and don't worry if you don't know about this notation, this is just standard notation for a translation surface. We can just call it S if we like. For those who want to know, X is a Riemann surface, omega is a holomorphic one form, but you can just think about polygons as parallel sides identified by translation. And we're going to form the translation prism, which is just S cross 0, 1 with x0 glued to x1. Right? So we're just going to take the prism and glue the top to the bottom. And in fact, if you take your polyhedron, which is P cross 0, 1, and you do unfolding, what you get is, well, slight lie here, you get, if you have the translation surface associated to the polygon P, you get actually S cross 0, 2 with x0 glued to x2, because you do the reflections in the polygon sides, and then you do just reflection on sort of the flat sides, the part staying on the x-axis, on the xy plane and at height 1 for the unfolding part of the prism. That's the only interesting thing you get in this vertical direction. Let me just stop here for a second. Does that at least vaguely make sense? That what you would get is you unfold your polygon, you get a translation surface, and then for the polyhedron part, the only interesting new thing that comes out is just sort of doubling it in the vertical direction. Is that okay with everyone? So maybe I started with my triangle, and I got to I don't know, it was maybe an octagon, and then I my prism over my triangle became a sort of a prism at twice the height over my octagon, which is going to be a disaster to draw. It's impressionistic, or I'm in France, I'm allowed to be impressionistic, but it's at kind of twice the height. Everybody happy?
Lots of nods from the audience.
Thank you, Noel. Okay, now here is kind of a general fact. So what we're going to do is we're going to just analyze linear flows on these translation prisms. I'm just going to call this is S cross 0, 1 with sort of, I'll just abbreviate it with 0 glued to 1 here. Now I have my linear flows on here, which will have, and what we're going to do is we're going to normalize them so we have sort of unit speed horizontally. So we have some horizontal direction, theta maybe, and then we'll have some vertical speed, which will be some parameter s. Right, so this is how, if there's many ways to normalize S2. We're not going to do unit speed. We're going to say unit speed in the horizontal direction. We're going to have a vertical speed S. Now, another big idea in dynamics is the idea of what's called the first return map. And a first return map is exactly what it sounds like. You take some subset and you look at, well, when the flow returns to it. And that gives you a map of the subset to itself. So what we're going to do is we're first going to think about the flow in direction theta on S. And, so I have some collection of polygons, this is, again, very impressionistic. And we're just going to flow in direction theta. And what we're going to do is we're going to take some transverse, we're going to just take some interval transverse to the flow. We're going to call it I. And the first return map to I is what's called an interval exchange transformation. IET is interval exchange transformation. And so now what happens if I add, now, of course, so this is literally the first return map is, I flow for some time. Okay, maybe I've missed it. Eventually I come back and I just see where I went. So this is a map T from I to I. And what is an interval exchange transformation? It's literally you take your interval, you cut it up into pieces, and you rearrange the pieces you cut it up into maybe n pieces of lengths, lambda 1, lambda 2, up to lambda n. And then you rearrange them using a permutation in SN. It's literally cutting up a piece of string and rearrange. So cut string, rearrange. And now I'm just going to, and now of course, if I have this first return map on the surface, I could also think about the first return map on the, I could sort of just take the I cross 0, 1. I could take this face, I can slice the prism, and I could look at the first return map of my flow, and I could say, oh, what time does it return to this face? So I look at, so
sorry,
yeah,
interrupting
please,
with
ahead.
a quick question from the audience.
Yes.
Hello. That's okay. I was just curious about when the first return map defines a cylinder. Like, is there a condition for that?
Yeah. So in particular, so we are going to be thinking about directions in this talk, which are ergodic or uniquely ergodic, in which case we will not have cylinders in those directions. But as you say, you can easily see directions. For instance, if you do the square, if you flowed vertically or horizontally, you would get a cylinder. The surface would become a cylinder. So basically, if you have a periodic orbit, you'll get an orbit, a collection of periodic orbits parallel to it. Periodic orbits come in parallel families, which foliate cylinders. So that's a really nice point. We're going to be thinking about kind of the opposite case, where most trajectories don't actually close up and kind of spread out evenly, in which case you will not see cylinders in that direction. But I've just packed a lot of hard math into a few sentences there.
It's looking good.
Good. So now what we're going to do is we have this map from I to itself, T. And now we're going to also have, if I could look at I cross, 0, 1 with opposite sides glue is just S1, and I can kind of look at T tilde from I cross S1 to itself, right? That's a map which is, I'm going to, sort of just see when I've come back to the space, right? So in this old picture here, it would be maybe I took some interval. I took some interval in my surface, and then I just kind of thickened it. And now I have a map from on this, the first return map. I flow and I come back to it. And now this is now where I want to introduce. This is what's going to be called a skew product. So let me black box something. So a black box, and this is a beautiful, this is a really incredible collection of results of Mazer and Beach in particular, is that in a very precise sense, most IETs are what's called uniquely ergodic, where uniquely ergodic means that Lebesgue is the only preserved. And so, by the way, since I started a bit late, can I go for 8 more minutes?
Yes, that sounds good.
Okay, thank you, because I do really want to get to this point of the story. So most of these T's are uniquely ergodic. So now, quick digression into classical ergodic theory. So if I have a transformation, which I'm going to just use, again, T, from a measure space, let's say omega to it. So omega is a measure space, is a probability space. So T goes from omega mu to itself. Mu of omega is 1. And mu of T inverse A is mu of A for every measurable A. So this is measure preserving. Let's carry this along with us. No. There we go. Okay. So we have that. Then we say T is ergodic if it's kind of irreducible. If T invariant sets are trivial, i.e. mu of anything T invariant is either 0 or 1. Mu of B is equal 0, 1 if B is T invariant. We say if we have a homeomorphism or a homeomorphism of compact metric space, let's say X to X is a homeo of a compact metric space, we say it's uniquely ergodic, if there exists a unique preserved 4L probability measure. Uniquely ergodic is really powerful because uniquely ergodic implies that if you, a consequence of this, a really powerful consequence is that if you take F from X to, let's say, R, which is continuous, and you start to average F, this converges to the integral of F, let's say probability measure, call it nu, d nu over X, for every X in X. This is really a consequence of what's called the Banach. Well, it's an application of the Banach-Alaoglu theorem about weak star compactness of the space of probability measure. This, I'll just mention above, is this statement star, even without holds for, if you have ergodicity, for F in L1 of X of omega mu, let me zoom in, but only for almost every omega in omega. So unique ergodicity gets you that every point spreads out. Ergodicity gets you that almost every point spreads out. Now, there's a couple of other beautiful, beautiful notions, which I think are not kind of as well known. And this notion is called weak mixing. And this is one of my absolute favorite, it's become one of my absolute favorite notions. So again, we're going to return to our situation of a measure preserving transformation. And now we're going to look at, we say, f from omega, f is in L2 of omega mu is an eigenfunction if f composed with, so let's say eigenfunction with eigenvalue c if f of t omega is equal to e to the 2 pi I omega f e to the 2 pi, not omega, excuse me, c f of omega. That is, so ergodicity was about invariance. This is kind of saying, well, this function isn't invariant, but it transforms in a way that I can understand. Okay. T is weak mixing if we have no non-trivial eigenvalues. Okay. Now, what's really, okay, this looks kind of esoteric.
Eigenfunctions?
Sure, but no non-trivial. I don't want any eigenvalues either, right? I mean, I don't want eigenfunctions or eigenvalues. It's, yeah, if I have an eigenvalue, I have an eigenfunction. We say, you know.
And you mean irrational, right? Because
I don't want any.
Wouldn't a rational eigenvalue give you a fixed point after, you know, an integral after finite number of steps?
Yeah, but I don't want integrals either. I mean, so weak mixing is gonna, right? So invariance, I don't want any eigenvalues.
Oh,
right?
okay.
So right, because in non-constant eigenfunctions, right? So let's say f is non-constant. I'll say here, f is non-constant. Okay, so what's amazing about this is this actually gives you a really amazing dynamical consequence. It says that if you average mu of t to the minus n a intersect b, n equals 1 to n, this converges. So this is equivalent to this. This is not trivial, and I urge you to try and prove this. This is in many classical ergodic theory textbooks, and it's not an easy proof, but it's a very, very cool result. This is kind of, and I'll just make a remark that says, there's also something called strong mixing, which just says that mu t to the minus n a intersect b just converges to mu of a, mu of b for any two nice sets. This says the two sets become independent in the long run. This says this is kind of a Cesaro version. But the cool thing is you can read this off using what these eigenfunctions. And now let me come back and I'm sorry, I'm just going to take a couple of extra minutes. I'm really, sorry about this, but I spent a little too much time on the unfolding, but I think it would be an absolute pity to do this without trying to connect, without giving you this construction of Furstenberg that I mentioned. So let me just try and do this quickly. So here, what Furstenberg tells you is kind of, it says, if I have some transformation, which is, let's say, ergodic, and I want to understand something about a skew product. So omega 0 cross S1 defined by T of omega 0 Z is T0 of omega 0, G of omega 0 Z. So that is, I do my transformation in the base and I twist in the circle factor by something. By the way, that is exactly what I am doing when I look at my first return map of my billiard or my linear flow to this interval. I get this interval exchange map twisted by something depending on the vertical speed. So now what I want to say is, so suppose I wanted to find what is an obstruction? An obstruction to ergodicity for t is an invariant function. Let's say f from omega 0 cross S1 to, let's say, C. If you have an invariant, a non-constant invariant function, right? So a non-constant. But now here's an incredibly powerful thing. So what would it mean for a function to be invariant? I want f of t0 omega 0 g of omega 0 z to equal f of omega 0 z. But now what I'm going to do is I have this S1 factor. I really understand S1 very well. In particular, what I can do is I can write f of omega 0 z in Fourier as a Fourier expansion, as a sum over all integers of some Fourier coefficient, which depends on omega 0, and then it's just z to the n. Right? This is Fourier expansion on the circle. But Fourier coefficients are unique. So star implies Cn of t0 omega 0, g of omega 0 to the n, z to the n, is equal to, well, forget the z to the n. We don't need that. That's I just care about the coefficient. G of 0 is equal to Cn of omega 0. And so what I get is I get this equation which looks kind of like the eigenfunction equation. In fact, this is in some sense, it's what's called a multiplicative co-boundary equation. And this is the key to this idea of Furstenberg, which basically says the ergodicity of a skew product can be read off from information about eigenfunctions, or more generally, co-boundaries for the base transformation. And absolutely, I can end in a minute. This is a really, really powerful idea. And what this allows us to do is this allows us to translate our results about ergodic properties of billiards in rational prisms to what are called weak mixing properties, weak mixing / co-boundary properties of linear flows / IETs on translation surfaces. And then we can use we still have to do a lot of work, especially for our explicit construction. But for our results about most, we're using crucially results of, and I really want to mention these names: Avila Forni, Avila Delacroix, and then very recently, this just popped up on arXiv, Arana Herrera, Forni, Chaika, and Forni. And these are incredible papers. But the takeaway I want you to take from this is, one, you start with this really, really simple problem about billiards and prisms. Turns out that problem is way, way too hard. Then you narrow down to a problem that you think you can answer, and you start connecting to all kinds of different pieces of math. And you get to make really cool, explicit pictures, and you get to make incredible connections to all kinds of different things. So let me just conclude by, let me actually leave the meeting from my Zoom here on my iPad, and let me stop by just showing you a picture with absolutely no comments on it. And then this is really where I'll stop, and I'm sorry for going over time. This is a cardinal sin, which one should never do, but I did. Just by showing you a cool picture.
Okay.
let's thank Jayadev. Unfortunately, we don't have time for questions.
I'm so
but-
sorry.
No, that's okay. Thank you for a great talk. Will you be open to answering questions via email?
Absolutely.
Great.
And I'm actually planning on sticking around and hanging out in the conference by Zoom so people can chat with me. And I'll drop my email into the chat as well.
Great. Thank you so much. Okay. It is my pleasure to introduce Sarah Cook from the University of Michigan, who will be talking about factoring Gleason polynomials, mod 2.
Hi, everybody. I'd like to say thanks to the organizers for the invitation to participate, and thank you all for being here. I'm gonna see if I remember how to, oh, can I share my screen? Oh, no problem. No problem. I can't seem to,